All right, let's get started. So first of all, thank you guys for joining with us today in this rainy and windy day. And here are two heads up. First, next week, Python's AI team will give us a talk to talk about their storage solutions on the LLM part. And the next thing will be, we'll announce our third assignment next week, probably. Okay. So the same things. Let me first give you some recalls about what we learned last week. First of all, we say before midterm, what we learned is there are process management and memory management part. And there are also some components in Linux that we are not going to cover, including the device control and networking part. So in the rest of this course, what we will focus on will be the I/O path, including the device block, device file system types, and then virtual file systems stuff. Okay. And before going on to more details, last time we clarify about the data. What is the data in memory? Because I think it is quite important for you guys to differentiate. Actually, we have storage and memory device, and you will put data on storage and memory device. So they look very similar, but in terms of CPU, in the perspective of CPU, they are super different things. Okay, because when we say the CPU, when the CPU running a process and it is going to access the memory stuff, actually CPU will use the those instructions. So let's say CPU can use load or store instructions to interact with the memory. And the thing is, if the requested data is not in the memory, then the MMU in the CPU will raise a patch fault. So it means like the patch fault means like CPU has the chance to run some other software stuff. So probably there will be operating system. So usually CPU will run the operating system, including the patch fault handler, to handle this patch fault. Okay, and after that, the data will be moved from like storage to memory, and then CPU can access the memory by using the load instructions. Okay. There is another way for CPU to interact with the data, as when the data is probably in storage device. And the key difference is, like, if the data is a file data, then your user programmer knows they are file data, because file, as the things like the CPU doesn't really know. File is a things is known by the user, because you store the data in the storage, you store data in the memory, and we call it a file. So when the programmer is going to access the file, they need to use the system code to let the CPU know, actually, we are going to get some very special things. Okay, the special things are those file stuff. Okay, so when the CPU decode the instruction and find like, hey, actually, this is a system code, then CPU will directly jump into the operating systems and then to run several stuff, for example, the packing, the file system, and the context switch. So if you're asking about what is the key difference between these two paths, I would say is for the left-hand side, the purely memory access, including you are going to access the heap, going to access the stack, those kind of things in the virtual memory space. Actually, CPU will use the load instructions. And if the program is going to access the file, so file is, I would say, like most of the things you are opening in your systems, there are file in most cases, like your multimedia, image, and songs, music, those kind of things. So in that case, what CPU will get is an instruction, and that is called a system call instructions. Okay, so you can also think about there is also a very special instruction called system call. Okay, I think I can put it like this. And we also talk about the data, just like what is the data? And the reason we talk about data is because we are going to start from our device part, like how to store the data. So data is a sequence of 0 and 1. And like in this image, there is binary image to like the grayscale images. So the only difference is how good quality the image is. So if you are saying about a black and white figure, it means you only need 1 bit. So to represent bit 0 or bit 1. And if you are going to get a grayscale figure, so you might need more bits because you are going to get more like better quality. You are going to differentiate from white, light gray, maybe the dark gray and the black part. So same things for audio. Audio is usually it is a signal. So actually we cannot directly store the signal in the storage or memory device. So a better way is we need to transform to some things that they can be represented by 0 and 1. So people usually use a sampling. So sampling is like, even there is a curve like this, then we only store several representative like points in this curve. So for these points, like we can use, like if you have more bits, then you can have more points, so you can have better close to the curve. And what we really store is this, like for this point, we will store it as a 0 and 3 ones, and this one is 0, 1, 0, 0. Okay, so what we will really store is these kind of things. And because for data, it is only about 0 and 1. So when you are talking about a storage and memory device, actually what they only need is a materials, and they can switch between 2 states, 1 and 0 stably. So all of the storage device and memory device follow this law. Just like hard disk drive, like we have magnetic fields switching between the parallel and anti-parallel. SSD cells that are high voltage and low voltage, and then DRAM there are capacitor charges or not. So usually they are binary, just like 1 and 0, like 2 different states. Okay, we also talk about the non-volatility part. So the key thing is it possible to keep the data even when we power off the device? So DRAM and SSD, those kind of, they're different stuff, because like DRAM, they are about when you power off your systems, and if there is no power to the DRAM, then the data will get lost. So it is volatile. And SSD, on the other hand, if you don't give it the power, actually the data will still be stored in there. So this is why we need storage device, because storage device in most cases they are not volatile. And when you are going to store your multi-data in some place in your computer, you need to store it in a non-volatile device. Okay. Otherwise, if you power off your systems, the data will get lost. Then we talk about there are 2 different very well-known devices, hard disk drive and solid state drive. And the key difference is hard disk drive is usually there are a lot of mechanical components inside. Okay. So components including the actuator, the bladers, spindles, and the rewrite arm. Actually, those are mechanical components. They will move it. Okay. Compared with hard disk drive, solid state drive, there is no mechanical components. So there is no motor, there is no this kind of rotating stuff, there is no moving stuff. Inside SSDs, there are only chips. So you can see there are all different kind of chips inside. So chips, you can think about, they are all about the circuit stuff. So this is the reason why the device called the solid state drives, because there is only like solid things, there is no moving things inside. Okay, we also talk about HDD, it is cheaper per gigabyte, and it is more reliable. The reliable is linked to, like, if you store data in the SSD, and if you have a good protection for this, if you store the data in the hard disk drive and you have a good protection on this hard disk drive, and this data can be stored inside for a couple decades. Like you can store it in like 100 years or even more than 100 years, it is possible. Okay. But on the other hand, SSD is not possible, because if you store data in SSD, probably like maybe 2 years or 3 years, your data will get lost. And this is because the nature of the SSD cells. So we will talk about this also later, why there is this kind of non-reliable things for SSD. Okay. And for the hard disk drive, I think a more important thing is the access model. So when we talk about the access model, it is about how to model in the disk performance. So there are three main components. The first is about a stick. So stick is about you have an actuator head and you are going to move forward and backward to get across different tracks. So one concentric circles is a track. So in this example, there are three tracks: the inner track, middle tracks, and the outer tracks. Okay, and if your head is going to move across a track, then it is called a stick time. And rotation is about actually the spindle rotates all the time. So like if you are going to get a sector 2 in this example, and the first thing that HDD will do is to stick to a correct track. So now the head is on track, the inner track, right? But sector 2 is on the outer track. So there is a stick time to move the head from the inner to the outer. And the spindle actually it rotates all the time. So the spindle can help the head to get the direct locations for the data. Okay, and actually stick time and rotation delay, they will overlap with each other because when you move the head, actually the spindle is still keep rotating. So it will be more like, for example, if the stick time is 4.9 milliseconds and if the rotation delay is another milliseconds, then we will get a maximum number between the two times. Then this is the time the disk head spends to gather data. Okay. Oh, sorry. One more thing. There is a thing also called transfer time. Transfer time is actually the stick time plus rotation delay is going to locate the head to the right, I would say like sector, because each of this is called a sector. So this is for getting a right location for the head. And then if the head is going to read out the data, then this is called a transfer time. Transfer time is, if you still remember, as when the hard disk drive is going to get the data, then you will give it a magnetic field to get all the data. Okay. So because hard disk drive is, there are mechanical components inside. So for example, if you can get the data aligned with the directions of the disk rotations, then you can get the data super fast. So for hard disk drive, sequential access is super important. And random access, it will be super slow because if we are going to move the head around this disk, then it would get a lot of time. So a better access pattern is to minimize the head movements in these situations. Okay, so for the transfer time, actually, if we look into more details about how hard disk drive works, then actually the disk head for hard disk drive, there are two different heads. One is called the write head, the other is for the read head part. Okay, so even this is a track, actually, the head will not really touch the track because the head is going to use the magnetic force to read out the data. So the smaller one is called the read head, larger one is for the write head. And because the size is different, so they are using different like physics characteristics to read out the data. Okay. So given we store the data on the track, then you can think like there are magnetic fields on this track. So if the left hand side is the north pole and the right hand side is the south pole, we will say this is the data is pole 1. And if in the reverse way, the left hand side is south pole, right hand side is north pole, then we will say this is 0. Okay. So for the read head, actually, it is using a thing called giant magnetoresistant technology. So for this GMR technology, the read head, there are two layers, free layers and fixed layers. So fixed layers means the magnetic field is always in the same directions. And the free layer, it is like, just like its name, it depends on the recording medium. What is the magnetic field of the recording medium, and the free layer will change the directions. So when the GMR device, when the GMR head, the read head, move through the recording medium, and according to the physics that we learned, actually, if it moves through the recording medium, then this FreeDARE will be sent according to the magnet for the directions of the recording medium. So now in this case, the FreeDARE will become the left-hand side is and the north pole, and the right-hand side is the S south pole. Okay, so because the left-hand side is N and right-hand side is S, so actually the FreeDARE, the magnetic directions of the FreeDARE is from the right-hand side to the left-hand side. Okay, so for the whole GMR head, actually, because the fixed there is in the same directions, and if the FreeDARE is on the opposite directions of the fixed there, then we will say actually this is called a high resistance step because there are different forces. So this will be like anti-parallel, and we'll say like this is like 0. Okay, so you can see like this is S and N 0. So this is 0, and if this GMR shows the anti-parallel magnetic directions, and we will say this is 0. So on the other hand, if the GMR moves through the recording medium as in this directions, then the FreeDARE will be sent to this directions. So because the fixed there and FreeDARE now is in the same parallel direction, so we can have a low resistance step. Okay, so with the low resistance step, actually, it will show the data here as data bit 1. Okay, and we say the right hand is using the things called inductive right. So inductive right in Chinese is 电流磁效应. So actually, given the current on this kind of wires, you will get the you will get a magnetic field. So with the magnetic field, you can change the magnetic directions for the recording medium. Okay, and this is also the reason why the right head is larger than the read head, because the magnetic larger the magnet is, so it can get a larger magnetic force. Okay, so with enough magnetic force, it will change the magnetic directions of the recording medium. Okay, so that is for the hard disk drive. So for the SSD part, it is quite different. And this time we say actually different kind of device, they are all using NAND flash, including the USB device, including the SSD, including what the memory chips in your mobile phone, in your Mac, in your Android phones. So the reason they are different, the reason you feel like the SSD time is quite different because USB is slower and SSD is faster is because they are using different quality of NAND flash. So SSD usually will use a better quality, and USB drive usually people use a lower quality of NAND flash. And because when you are using a lower quality of NAND flash, you might need some extra software way to handle the error. Because lower quality means when you are going to read out the data and there will be more noise, there will be more errors, so you cannot get the right data. So you need to for example, do some ECC or to do some any kind of power correction to recover from those kind of noise. Okay. So we also show you actually, we say for the SSD, they are a couple of layers inside SSDs. And I think the most important thing is in your SSD, there are controllers. So controller usually means the micro CPU part. And then there are also DRAM. And the DRAM actually is not in a very small size. Usually the DRAM inside SSD is quite large because in SSD, it needs to store the mapping table in their DRAM. So you can think about if you have like, for example, 1 terabyte of the SSD, then you will need at least 1 gigabyte of the DRAM. So the larger the SSD capacity is, you will need more DRAM in your SSD to store the mapping table. Mapping table stuff we will talk about it later. Okay. So for the architecture, actually, it is like this: the channel, chip, die, flame, slot, patches, and cell. So you will be born like this kind of expansions. Okay. So why it is so many expansions is like actually different label. It depends on For example, if the data is on different channels, then you can get the data in a parallel way. Because come to think about, if your data is in this die and this die, actually they are on different channels. So you can send the data in the same time, right? But if your data is in the same like in the same chip, then the parallelism will not be that high actually, because you share the same channel. So when there are too many data, they are sending across these channels, then there is congestions for this kind of data transfer. Okay, so there are also more details like for patches stuff. So this is more technical stuff for the patches and block. So given this is a block, so actually for each word line means a patch. So this patch is not the same with what you learn from like the virtual memory management part. It is not that always patch. This patch is dedicated for the SSD. So in SSD, they also call it patch. And the size, usually it will be 4 kilobytes to like 32 kilobytes, depends on different manufacturer and different generation of SSD. Okay, so this word line actually for each block in general, you will get 512 patches in each block. So if each patch is 4 kilobyte, and if there are 512 patches, it means your block will be 2 megabyte. And the reason like there is a block structure is because for SSD, it erases the data in a block granularity. So the thing we say in the block granularity is you can only erase the minimum unit for erase the data in SSD should be a block. So you cannot erase a patch in SSD, because when you are going to erase a patch for SSD will directly erase the whole block. Okay. There is also another thing is patches. And patches is when you are going to rewrite the data, the minimum SSD granularity will be a patch. Okay, so today we'll talk more about a memory cell. Just like we say the patch is 4 kilobytes, so it means it stores a lot of bits inside. And today we'll talk more about how SSD can store a bit, how to represent 0 and 1. And this structure is the floating gate structure for the NAND flash cells. So you can think about like this memory cell. If we give you a more realistic figure, it will be more like this kind of stuff. So there are P subtract, and then upon P subtract, there is floating gate and control gate. Okay, and P subtract the Chinese, I think it should be like P 型基值, something like that. Okay, so you can think about like for SSD, they are the number of electrons inside this floating gate. It represents it is 1 or 0. So if there are a lot of electrons inside this space, then we will say this cell represents bit 0. On the other hand, if there is no electron inside this space, then we will say it is about the bit 1. Okay, so it is quite simple. But how to approach this kind of different steps? How to approach bit 0 and how to approach bit 1? Okay, so we give you a quite mapping. This is the floating gap that you see in the prior slides, and this is the things you usually will see later. Like this is a memory cell, so it will be like this. We rotate a minus 90 degree, so control gap and P subtract. This is control gap, and this is P subtract. So this one is a word line, and this one is a bit line. Okay, so it will be more like this. This one is a word line, and the vertical line is a bit line. So the intersection for each horizontal and vertical line, it will be a cell. And this direction here, this will be the control gap. And here will be the P subtract. Okay, so the mapping is like this. So when there are electrons inside the floating gap, it means there is the voltage inside the the floating gap. So if we apply the voltage on this structures, actually what we will see is there will be no current be passed through this piece of thread, which means if you give this wire line a 2.5 grid voltage, and if you already have some electrons inside the floating gap, the current will not pass through it. I mean, the current will just stop here. Okay, and we'll let you know the reason later. So on the other hand, if there's nearly no electron inside the floating gap, then if you're using the same voltage value, we say 2.5 volt, you will get the current pass through this pass through this nameplate cell. So this is the reason why there are two stats, because if the floating gap inside there's electrons is in the high voltage value, then when you read the data, the current cannot pass through. But if there is nearly no electron inside the floating gap and you use the same voltage value, then there will be current pass through this nameplate cells. So if you have some sensing components, sensing circuits at the bottom here, then you can know if there is no current, then you will say, hey, this is bit 0. And if there is current, if you receive the current value, then you will say, hey, this is bit 1. Okay. So let me give you more details about why, like, if there are electrons inside the floating gap, then you will not have the current pass through. So the very beginning thing is we'll first talk about program, or usually you can think about it, you are going to write some data inside the nameplate cells. So program means to push the electron from P substrate into the floating gap. So you can think about, actually, currently for a nameplate cell, there's only two stats. Like there's electrons inside and there is no electron inside. So the program, at this moment, the program is only to push the electrons from the P substrate into the floating gap. So like this, if you apply a 0 volt, like the ground voltage for the P substrate, and then a 20 volt for this control gap, and because when you apply a 20 volt on this P substrate part, then there were delocalized electrons will become excited. So you can think about like this. There are several electrons become excited because you apply a 20 volt here. Okay, and because 20 volt is a higher voltage value, so because with this high voltage, those delocalized electrons can get enough energy to jump through the dielectric layer. So dielectric layer is a kind of insulator. So in Chinese, you can think about it is called 介电子, and 介电子 is kind of 绝缘体, but this is a spatial 绝缘体. Okay, so in general, actually, if you don't apply this high enough voltage, the electron cannot cross through this insulator because, I mean, by nature, it cannot cross it because it doesn't have enough energy. But because 20 volt here, you can think about it's a very high enough energy. So those delocalized electrons will cross through the dielectric layer into the floating gap like this. Okay, so this is how the nameplate cells can, I mean, there's a possibility to gather electrons inside it. Okay, so the reason nameplate cells can be a non-volatile device, the SSD, the reason it can be a non-volatile device is they use this dielectric layer to insulate the electrons to avoid those electrons to flee off. Okay, so if you don't give it any energy, actually, and those electrons will not have enough energy to pass through this dielectric layer. So you can think about if there is no power, there is no power to apply on these nameplate cells, then the electrons, they are captured in this floating point. So they cannot escape, they cannot flee. And this is the reason why even you don't apply any power source to this SSD device, the data will be still there because this kind of these electrons cannot get out if there is no enough energy. Okay, so you can also think about this is called program. So if you are going to get like bit 0, it just means you don't do anything, because you don't do anything, then there is no electron inside this Cohen gap. So this is quite simple for the SSD, just like you use a program or you don't use a program, then you will get like bit 1 or bit 0. Okay. Okay, I think program is quite intuitive. Read will be a little bit counterintuitive. Okay, so when we are going to read the data, actually it depends on, can we receive the current? Can we receive the current from this NAND flash cell? So what do I mean can we receive? In this case, we will apply a relatively small voltage value. So in this example, we take 2 volt as an example. Okay. So when we apply 2 volt, actually, we will the same things. We will activate some very few. Sorry, we will activate very few delocalized electrons from the P substrate. And because there's only 2 volt, so which means those electrons cannot get enough energy to cross through the dielectric layer, right? The reason in the prior example, the reason the electron can cross through the dielectric layer is it gets 20 volt. So 20 volt is a super high voltage, but 2 volt is too small. So this 2 volt cannot let this electron to get through the dielectric layer. So in this case, these few electrons will be captured from N source and N drain. Okay, but because we only get very few delocalized electrons, so this electron cannot generate a current, because when we say a current, it's the moving electron, right? But if we are going to get a current, it means we need a good amount of electrons that can move, so you can have a current. If you only have a very few amounts of electrons, then those will not generate the current. So because there are too few electrons here, so there is no current. Okay, so does not have enough electrons. Okay, we have another scenario, because we say we use a program, so we move the electrons inside the Cohen gap, right? There is another version is we don't apply any program, and this is another bit step. Okay, we apply the same voltage 2 volt to these situations. Okay, in this situation, actually, if you look at the P substrate, you can find there are more electrons being activated. So the reason is, you can think about the reason is because for this scenario, you first apply 20 volt and you apply 2 volt. So when you apply 20 volt, there are more electrons be activated. So when you again use a lower voltage, you can only get a very super few amount of electron. But on the right hand side, because it doesn't apply any high voltage value beforehand, so when you once apply 2 volt, actually you will get a little bit more voltage value. So sorry, you will get a little bit more electrons in this case. And the same things, because those electrons cannot cross through this dielectric layer, because 2 volt is still not enough energy to drag these electrons to cross through the dielectric layer. So you can think about, now the electrons will be once again captured by the N source and N drain. But the different story is because there are enough number of electrons, so it will generate a current from N source to N drain. Okay. If you come back to this example, N source is here, N drain will be here. So if there is a current, then the current value will pass through the bit 9. So this is called bit 9. There is a wire called bit 9. So for this bit 9, if there is a current value to move through the end of the sensing unit, then the sensing unit will tell you, hey, actually this memory cell, I mean, there is no electron inside the Cohen gap because the current can pass through this memory cells. Then we will say, hey, then you are like bit 1 or bit 0. So it depends. I mean, it is bit 1 or bit 0. Actually, it doesn't have a very static mapping. It can map by the device itself. So what you only need to differentiate is if there are electrons inside the floating gate or not. Okay, so this is about read and write. So one note here is higher voltage values induce more electrons from the piece of tray. And the number of exciting electrons is correlated to the voltage value. So this is the reason when we apply 20 volt, there will be a large amount of the electrons. But if we use 2 volt, actually you can get only a few amounts. But if you first use 20 volt and then you use 2 volt, you will get very least amount of electrons. Okay, so this is the idea behind to program and read. Question for this part? Okay, so I'll move on. Okay, so we talk about the program and read. And the next thing is, but how to drag off? I mean, how to remove the electrons from this floating gate? Because we say this is a dielectric layer, right? So if we don't apply any energy, the electrons will stay inside. You can think about like forever, ideally. But it doesn't forever because there are some reasons later I will let you know. Okay, so if we are going to drag off less electrons from this cell, we are going to do a reverse things. We will apply the minus 20 volt from the piece of tray, and we'll give a 0 volt from the control gate. So in this way, those electrons will be dragged off and then will be flee from the end drain. Then they will get off, then there will be no electrons inside. So this cell will be, you can think about this cell will be once again becomes a state with there's no electron inside. Okay, so this is the reason why the erase granularity is a plot, but the rewrite is a patch, because the erase operation is going to apply a super high voltage value on a piece of tray. So because actually I didn't put a very circuit level figure here, and you can image actually on this piece of tray, actually there are a lot of this kind of floating gas cells. I mean, you can think about piece of tray, maybe it's like a square panel there. And then on top of piece of tray, there are a lot of control gate on it. So when you apply the minus 20 to this piece of tray, actually all this kind of floating gas upon this piece of tray range, they will get the same minus 20 volt. So all those kind of cells, they will drag off the electrons from it. Okay, so this is the reason why the block should the erase should be a block, because this one is directly applied to piece of tray, and piece of tray is quite large. I mean, you can think about piece of tray maybe it's this large, and then there are a lot of floating gas on it. So once you apply the super high voltage, all the floating gas on this piece of tray will get the same minus 20 volt, and all the electrons inside those floating gas will be dragged off. Okay. So this is only just to let you know what is program and erase. So initially there will be no electrons inside all the floating gas. So initially you can think about all of that, it is called bit 1. Okay, and if you are going to switch bit 1 to bit 0, what you are going to do is to do a thing called program. Program is going to push the electrons from a piece of tray into the floating gap. So then you will have good enough of the electrons inside the floating gap. So you will become bit 0. Okay, and a reverse way is to do the erase, because erase is going to drag off the electrons from the NAND flash cells. Then you will go back to the big one. Okay, so this is how program and erase works on the NAND flash. Okay, but I think this is not real enough because this is only 1 bit, right? So I think you will be more curious about if there are more bits. For example, we say the program should be a patch. A patch, there are 4 kilobytes. So 4 kilobytes, you can think about there will be 4K, 4096, those amount of the bits, amount of cells. So you can think about, I give you a little bit close to the realistic example is if there are patches, we say each 4 line in the, once again, each 4 line in this kind of diagram, it is called a patch. So on the 4 line, there are a lot of memory cells, okay? So I use the same example here. This is first patch, second patch, third patch, and the fourth patch, okay? And on this patch, there are memory cells. So inside the memory cells, actually, if there are electrons, then there will be a high voltage. If there is no electrons, then there will be a low voltage. So in this first image, if there is a patch called patch 2, and the state of patch 2 is there are O1. So 1 means there is no electron inside the floating gap, right? So you can see like the voltage now inside the floating gap is low. It is only 1.9 volt. Okay. So our goal is to do the program. We are going to program this 1111 to 1100. Okay. So 0 means we are going to move the electron. We are going to push the electron from P substrate into the flowing gap. Okay. So what we are going to do is the same things. We will apply a super high voltage, let's say 20 volt here. Okay. So this 20 volt is applied to less directions. So this one is the control gap. So if you still remember, actually, this one should be rotated at minus 90 degrees. So this control gap actually is here, and this one is P substrate. So if you apply if you apply the 20 volt on the control gap, actually the P substrate will be activated a lot of delocalized electrons, and those electrons will be dragged into the floating gap. But here comes a problem, because the 20 volt will be directly applied on the 4 volt line. So all the memory cells on this 4 line will get 20 volt. So by nature, all the memory cells will all be programmed from 1 to 0, right? Because if you apply 20 volt to this wire, then all the memory cells, their P substrates will be activated, and the delocalized electrons will be pushed into the floating gap. Then there will not be 1100. There will be 0000. Okay, so this is not enough. We also need to apply another directions of the voltage called inhibition voltage. So inhibition voltage is you can think about is to avoid some memory cells to be programmed. So if you apply the inhibition voltage for the first 2 cells in this directions, okay, then the first two cells will not be programmed. What we only do the program is the last 2. So you can see the last 2 from 1.9 volt becomes a higher voltage, 3.1 and 2.9. Okay, so what happens? Why you apply the V inhibitions, the first 2 cells will not be programmed? Okay, it is like this. Like this one is a 20 volt here. We apply the 20 volt, and these cells you can think about maybe it's this cell. Okay, so the P substrate here is here, and you apply 20 volt, then you can think about there are good amount of the delocalized electrons be excited, and those excited delocalized electrons will be pushed into the floating gap by nature. But now, if you apply this directions of the voltage, this is a 5 volt voltage. So in this example, actually, the electrons cannot cross through the dielectric layer, because there are different directions of force, right? There is another force from the horizontal side. So those electrons cannot have enough of the right directions of the energy to cross through the dielectric layer. So they will be dragged off by this directions of the voltage. Okay, so these electrons will be directly go through the end drain and they will get off. Okay, so this is the reason why if you directly apply a inhibition voltage on the bit line, then the corresponding memory cells will not be programmed. Okay, so that is for program. So now you can think about, now this one is 1100. Okay, and Next step is, but how to read out a data. So, oh, sorry, I missed one thing. So the reason, okay, so the reason when we are going to write the data, we are going to apply the 5-volt on those kind of all the patches is because actually 2-volt is super high. And you can think about this is like a circuit, and then those wires, they are very close to each other. So when you even apply 20-volt on this wire, actually there will be they will affect the other word line, because this is the high energy. So the other word lines will be affected. So if you don't apply a pass-through like 5-volt, probably for some cases we will face the things called disturbations. Okay, the disturbations means there are some enough of the energy will affect the state of the memory cells. For example, maybe if this is 20-volt and you don't give it 5-volt, and maybe there are some effect will happens on those kind of memory cells, then their electrons, some will be flee off, or maybe some memory cells will get extra electrons. Okay, then they will affect the result for those kind of memory cells. So there is a pass-through 5-volt when you are going to do the write. Okay, and on the other hand, when you are going to do the read, actually, assuming we are going to read out the patch 2, then we will apply a super low voltage value, let's say 2.5, for example. Okay, so once again, we will apply 5-volt for the rest of the patches we're not going to read. Okay, so it will be look like this kind of stuff. So the reason we are going to apply the 5-volt is because actually 5-volt is quite larger than read voltage, right? So you can think about if we apply 5-volt here, let me show you, I think would be this example. Okay, if this one changed to 5-volt, then no matter you apply 20-volt before or not, there will be a good amount of a good amount of the delocalized electrons will be excited on this piece of thread, because 5-volt is twice more than 2-volt, so you will get a lot of electrons. So no matter there is things inside or not, there will be current value. Okay, because 5-volt is larger. So you can think about, actually, if you give it 10-volt, 20-volt, 30-volt, actually there will be more electrons will become excited on a piece of thread. So probably there are current value here. But because if you use too high of the voltage, I mean more than maybe 10 or more than 8, then those electrons will be higher chance to directly cross to the dielectric there. Okay, so actually, how much of voltage it should be very sophisticated decided from the manufacturer side. They need to do a lot of testing to know, oh, actually the beam rate should be 2.5 or something. They cannot be too high, because if it is too high, then it will becomes the program operations. Okay, so 2.5, the same thing, because if this is a lower voltage value in the volume gap, it means there is no electrons. So it means we did not actually have applying the high voltage beforehand. Okay, so if we use a 2.5-volt, and for this case, there will be like a good amount of the electrons to be excited, then there is a current value. Okay, and for this case, because you already apply a higher voltage, so some electrons, they already be dragged, they already be pushed into the voltage gap. So in this scenario, if you apply 2.5-volt, these cells does not have enough of the electrons can generate a current, so they will stop here. Okay, so at the end of the circuit, usually we will have a sensing circuit to sense about, oh, actually we get a current value, no current value, no current value. So if there is no current values, we know this is in a high voltage state, so it is bit 0. And if there are current value, then it means there is no there is no electrons inside the voltage gate, so it is bit 1. Okay, so this is the way how to read out the patch. Okay, so recall erase granularity. So because when you are going to erase, then it should be aligned with a block size. So a block size is 512 times larger than a patch. So here comes a challenge. if you are going to do the erase, and then you should do the you should avoid to do the erase all the time because erase unit is larger than a write. Okay, so for example, if you are going to write, you are going to update the data in this patch, right? Then you cannot directly update it because if you are going to write it, then you need to erase first. The reason is when we say we are going to do the program, it means we are going to move the electrons to push it from outside to inside the floating gate. Okay, so if you program one time, and if you are going to program the second time, actually the electrons are already inside. So you have no chance to do the programming. Okay, so for each time you are going to do the write, actually you need to first do the erase. You need to let the patch to go back to the origin step. That is nothing inside the floating gate for those cells. Okay, so because erase unit is larger than write unit, so what people usually do will do the will need to be constrained by the sequential write constraint. You cannot write the same patch twice, generally. Okay, I think we can take a pen and we'll come back later.哦，对，
那个后期是 HD，像这边的话，有两个小问题是内圈跟外圈的那个大小是不一样，所以它的 sector 里面是都会不一样，还是它就是会切成像这样？
它有两个模式，一种就是就像这样子，
嗯，
就是它都是一样的，因为这样它比较好管理。那有另外一种做法是，它会切成不等大小的，然后它叫什么 Zone Bit Recording，就是 ZBR。那这个做法，因为它内圈会切出比较少，外圈切出比较大，所以它需要有一些额外的这个就会去维护说，那为什么外圈比较大？那比较大是多大？那会有多少个 sector 在外圈这样子？
那维护这个的话，基本上是只能靠 OS 维护，还是它？
哦，没有，它这个维护是在 HD 里面，HD 也有它的小的 controller 跟它的敌人。
哦，它里面有敌人。
对，所以它也会去记录说里面大概有多少。
如果它里面有敌人的话，那它应该会有 ROM 吧？不然它怎么样把它的 driver？
对，
哦，所以就是它会先把 ROM 连上的话，它会先把这样，然后去出出它的 page table，也是放在它的敌人里面，对不对？
对，但它比较 page table，因为毕竟它自己回去，对，但类似
page table，
对，但它不会那么复杂，因为它基本上就是可以告诉你说，它的分法器就是它会切几个 zone inner zone 它可能就是固定就是一圈就是几个 sector，所以就算你今天这两个 zone 都被归在一层 inner zone，但你外面的比较大，你还是会只能跟里面有一样的多。对，
了解。然后 net SSD 的话，我想一下，哦，之前是说那个它可能过2年或过几年之后，因为当中的电子是不是就会直接跑掉？对，
就有可能会跑掉。
对，那如果这样的话，那再重新接上的时候，那些资料是会直接视为什么？它会直接
就是直接读，就读出来就会错的，
就是很奇怪的东西。
应该说它读出来跟你当初就是用 ECC 存的那个会对不上。所以他可能会用 XOR 之类把你现在资料跟你过去存的那个版本去做 XOR，
对，
然后你这个 XOR 出完就发现它可能有很多笔都是出错的，
对，然后它就可能会，它会坏轨，
类似就是看错多严重，如果它可能只有错什么几个 bit 而已，那它就可以被 ECC 回来，但如果它错太多的话，就没办法被复原回来。
那我这边就想说比较好奇一点，就是说，那假如说过很久，对不对？它那在 SSD 里面是不是有时候会去标记说，把那个 HD，它也会标记说这个可能这个 cell 坏掉。
没错，它会叫它 bad block。
对，black block。那过了很久之后，重新插上之后，这个 black block
还会在，那个记录还会在。
那个 flag 它是记录在哪边的？
就是它可以直接记录在那个 nameplate 上面，也可以在 ROM 啊。但是如果它这个东西大之后，它就会需要记在某个地方。那因为 nameplate 本来就是
它会直接记在 cell 上面。
对。
它直接
它可以直接记在 cell 上，
可是不是说过了几年之后那个电子都会跑掉？
没错，
怎么记？
因为那个 cell 其实有分就是 quality， 它可以用比较好的 quality 的 cell 来去记这些资讯。就是 SSD 的寿命，它其实是根据
它的那个刚刚那个介电子的那个，
没错。然后还有就是你的 program 方式，因为现在我现在都只讲到它里面都是有或没有，可是等一下会讲到说，它可能是要表示多个 bit，那你要表示 bit 越多的话，那你就会需要去 program 越多次这样子。
所以你要存越多，就是可能性在同一个空间里面的话，你就会影响到它的寿命。
就是因为就是简单来说，中间这一层会很容易被打穿这样。
是哦，没有，它是同一个，只是因为你要去控制电压到刚好这样子，你会需要去打很多次电压。
它只是控制电压而已。
对，
因为
控制电压。但你控制你打一次，它就是代表有一些电子穿过去，只要有电子穿过去，它就可以直接变波，这样子。
所以1跟0就是现在是讲只有1跟0的那个理论上寿命是最长的。
没错，所以对他讲的就是可能有3 base 这种，它就是
扩抓跟那个
很多次，对，那它就会出现说，当然你如果都是用 SOC 的话，其实它的寿命不会太大问题啊，因为 SOC 寿命其实会很长。但是你今天如果是什么 QoC，你可能只有1年或者甚至几个月，那你就可以用这种 SOC 去帮它去做。
但不管是那个颗粒的那个问题的话，它还是有可能说过几年之后它的电池跑掉了。那这样的话，它的 black box 是要怎么记录？
就是颗粒的问题的话，就是它会用就是这种 SOC 这种一个 bit 的方式去记录那一些 bad block。对，因为毕竟在很多就是
其实
高容量的状况下的话，它的 bad block 可能会很多。
那它是可能一个 page 只要记录，它是black block，它是直接记录一个 block 还是一个 page？
它通常是记录一个 block。
所以其实只要一个 block 里面的可能几个 bit 活着就好了。
对，没错。
了解。
当然，它还有很多，就是它也可以用 ROM 嘛，就是这种，我觉得就是他们看 SSD 还要花多少成本在这个面向上面。对。
那 HDD 的那个 DRAM 的话，它基本上也是根据说它的那个容量的大小去做，就跟它 sector 有多少 sector 去做比较。
我觉得可能不会，因为它的 sector 数目
很多，
就是它不会真的需要去把每个 sector 都记下来。它只有在那种很特殊，就像你刚才说的，它如果每一圈它想要有不同大小的话，那它怎么去知道哪一圈是大，哪一圈是小？它就在这种时候会需要记这种额外的资料这样子。所以 HDD 通常它的 DRAM 不会那么多。它就是很特殊用途的时候，它就会有DRAM存在，然后不然就是作为 buffer 使用这样子。对，就是你把资料读出去之前，你可能会需要进入那个 DRAM，然后去做一些不知道检查有人没有。
那它会不会有什么类似 TLB 的东西在 DRAM 里面？那我觉得 SSD 里面应该有类似 TLB 的东西。
也没有，因为就是 TLB 它其实是为了 CPU 去特化出来的一个架构，然后那原因是因为你要做 virtual to physical 的转换这样子。那 SD 基本上没有 TLB 原因是因为 TLB 很贵，因为 TLB 是 SRAM 的。对，所以当然你说可不可以有？当然可以有，就是它是
避免 miss 吗？
就是对，就是你要避免 miss 的话，它可以有。可是这个
太贵，
就你可以想一下，就是说对于 CPU 来讲，它为什么要 TLB？是因为 CPU 的运算是非常快的。那你今天停在那边，就它就是 idle。可对于 SSD 来讲，它那个 control 就只会做查找的动作，它没有别的任务要做，所以它就算稍微慢一点，其实也还好。那而且问题点在于 SSD 的资料读取是很慢的，所以你今天只要开始读一个 page 之后，你下一个 request 找进来，你可以去判断下个 request 在哪里。那你下一个 request 在哪里，你可以找很久啊，因为毕竟你 SSD 读一次跟你的 controller 找一次，可能差了应该至少10的54方到10的60方的差别。对，所以有 TLB 基本上它会有效果，可是它在那个情境底下会
那个
CP 值不高。
那个效益没那么大。
对。
那个为什么我就是用那个报告的时间，好，另外再就是如果表放的时间，因为我后来发现我原本约那时间我刚好要期某一科刚好要期末。
那你就寄信给我，然后我们再约一个时间这样子。
好，因为我上次有寄信，但我就是没有，要帮我再寄一次。
好，我再寄一次。
我再寄一次。
好，
谢谢。
我想问，就是为什么上爬就是查到这两个区别，然后他是说就是这个都只会在 user space，但是你讲一点不是话，它是会往下这样找，然后还做 context switch 啊。
user space 没错啊，因为它一开始触发的时候才 user space 触发的，就是你的程式在跑的时候是 user space 跑。可是假设你今天要去楼搜那一块记忆体不在，就是它的资料不在你的 memory 的话，那它就会下一步它就会触发 kernel 的操作这样子。对，所以你那个 instruction 在那个当下确实它是先是经过 user space 去做的。对，因为你跑你的程式嘛，你跑程式你是用一个可能就是要去存取一个你自己宣告的 heap 的 的地方，就你可能用 memory location 去告它，那要训练它，那这个存取它就是一个 low 的 instruction。可是问题点在于，这个 low instruction 它很有可能遇到的问题是它没有去对应到后面有资料，因为它可能是 on demand，或者是刚刚好它可能资料被 freeze 掉了，所以它的下一个 instruction 就会很有可能会是要去进 kernel 做事情。
所以对，啊，所以它这个东西它也会，它也会有 content switch 嘛，可是它不是，它不是就在 user space 的话，
哦，没有，这个是你在 user space call 这个 low store。好，你 call 的时候呢，基本上你会遇到一个事情是你要去转，就是去确认说你那个资料有没有在那个地方，因为你是个 low 的嘛，然后你 low 的时候，你会去确认说你这个 memory 到底可不可以被使用
啊，
对，那你的 memory 如果 permission 有问题之类的，那你 CPU 就会因为你 permission 有问题，CPU 就会从 user space 跳到 kernel space 去，
所以它会转到 kernel mode，
对，它就转到 kernel mode，然后去做运行。
然后它也会
kernel mode 的话，基本上就有很多可能性，那这个是 page board 的一个可能性而已。对，
哦，所以它不会就直接就没有就是没有拿到，
没有啊，他们那这样电脑就不会继续好了。就是如果你今天没有这一块的话，那你的 load 很有可能，例如你可能刚好要 load 的一个资料是在 storage 的话，那 CPU 就会完全不知道它在 storage，CPU 就直接读它。CPU 直接读它的话的问题就在于 CPU 就在那边等很久，那你就发现电脑就会当在那里。
哦，
对，
好，所以就是它没办法，它本身 memory 没有的时候才会，
就是它的资料不在 memory 的时候，或者是它的对应关系没被建立的时候，对，反正就是 page4 那些原因就会是其中一个，使它要进 kernel。
那刚才就是，我想问，就是说它这里为什么会说是高电位？因为它中间不是就是充满就是电子嘛？
对，高电位只是它里面都是电子，但
它不是实际上的高电位，因为一般不是说电子越多，它是比较低电位。
哦，对，这个其实示意跟大家说，它这边是指的是它的内部电子数目比较多。对
所以
它不是
应该要
真的
改成
是
对
单 volt。
对，它不是对，
所以这张图上面
这些
那个
数字
都是
都是对，就是类电子数量，这些数都只是示意跟大家说它是代表电子数目比较多这样子。
所以只有那个排线的那个 voltage 才是真的 voltage。
也不是，那是排线的 voltage 是有点像是概念，让你们知道说它是比大小的关系，就是可能 program 的时候它可能是20，然后那个 read 的时候可能是2.5之类的，它是有一个差距在。但是实际上的 SD 到底是几够的，是很看当下的，就是他们在做的时候，因为毕竟你的拉线那一些的，然后你的 page size 都会影响到它要几够的这样子。对，
所以只是差距的问题。
对，这只是让你们示意他说它就是大概会比它高很多。
但这个正负应该是
正负是
对的，
是对的，正负
只有那个
对，只有那个部分的，对。
那刚讲到就是它这个20伏，它会影响到旁边，
对啊，
这
20伏特就是它会有干扰，就是你今天如果给它一个高电压的话，那你周围的人就也会被干扰到。
这类是感应的问题吗？
就是它是因为它会有电场，所以它会影响到周围的那个，
所以我不 apply 这个商品会不会它的电场一样的？
对。
那个被影响会怎么样？就是
它就是有可能它的那个原本你今天它是这个电子数目，它可能会增加进去，就你原本可能是近乎空的状态，但是因为你这边用个高电压，所以这边可能也被影响到。那有些是空的，近乎空的这个 cell，它就会有电子就会跳进去这样子。
好，
对，然后它就造成状态，
因为他们很近。
对。就如果它是因为它是讨论2D 的状况，所以这个状况文献的说明是没有到这么严重。那如果是3D 的话，这个问题就会很严重，因为3D 还会有上下的干扰存在，
但是还会再往上爬。
对，所以它是一个就是你可以想象成一个3D 的干扰。
那个 kernel space 的东西，我想再理解一次，就是它进 kernel space 之后是去处理什么东西？
就是其实进 kernel space 这件事情，你可以想象它就是一个 CPU 状态的转换而已。今天一开始它做 load store 是 CPU 一个 bit，它就是在 user bit 的状态这样子，就是去示意说你现在这个是个 user 的 process 这样子。可是 有任何的例外发生之后，CPU 的状态就会从 user 转成 kernel，就是原本它是不能跑 kernel 相关的任何的服务的，但你今天如果透过 bit 的转换，让它变成一个就是 kernel state 的状况的话，它才有办法去执行做一些事情。所以你可以想象成是任何只要有例外出现，有什么资料不在啊，资料的 permission 不对啊，这种都是叫例外状况，那它就会进 kernel mode。那至于进 kernel mode 要跑什么东西呢？多半的时候是它会跑这个，因为如果是 page four 的话，它就跑 page four handle 的；那如果是别的 fold 的话，那就跑别的 fold handle 的这样子。对，这个如果要有一个更具体的 example， 你可以想象成说，你要 load 一个那个 address， 那你这个 address 原本在你的 program 里面是个 virtual address， 所以你会需要透过 MMU 比如说转址，你要先知道它的 physical 在哪里。MMU 在转址的时候就会发现你这个地方会转不出来。MMU 如果转不出来的话，它就会去触发 CPU， 跟 CPU 说这个地址有问题。CPU 知道这个接到这个之后，它就会去把这个漏受给它停住，然后去把那个状态切换到 kernel 的状态，然后它就会有一个机制是，因为你这边是 MMU 发生了 page fault，所以它会知道说你现在 CPU 下一步要去走哪一个方向去跑。对，那因为它是 page fault，所以它所指的 function 就会是 page fault handle 的 function，CPU 就跳过去执行那一段程式码这样子。对，然后那段程式码呢，因为它是高权限的嘛，它要 kernel 才帮它执行，所以这是为什么还要转成 kernel mode 才帮它去执行。
对，所以假如说就是他 raise page mode 之后，他进入那个 kernel mode，然后去跑 page fault，然后假如说它是有东西在 storage 里面，不在 memory 里面，那如果我要用DMA 去拉东西，它也是先进这个，然后叫 DMA 去做，然后再跳回来。
没错，
所以才会进这一段。
它不一定会跳回来的，就是这边 page swapping 这块就是你说 DMA， 它会去控制 DMA 跟 DMA 说你要把哪段机体分到哪段机体之后，然后它可能就会跑 context switch， 所以它就直接把这个 user process 直接 switch 出去，让这个 CPU 可以跑其他人。因为你用 DMA 搬的话，你还是要等资料吧，你只是原本你的搬动是 CPU 要去帮你一个一个资料把它搬。你现在是把这个工作交给 DMA 做，可是事实还是资料不在那，所以这个 process 还是没办法继续往前走。
所以这边的 context switch 是指因为前面一个 user 他的东西还不在，
没错，
所以他要跳给另外 process， 对，所以才要做 context switch。
没错。
好，那我知道没有。
对，
好，下次。
好，下。All right, so let's come back. Okay, so we say the erase unit is 512 times larger than the write unit. And we also say when we are going to rewrite the data, for example, if you write the cell at the first dash and you are going to write it twice, write it third, actually you cannot write because the stat is already changed. I mean, the electron is already be pushed inside. So what you are going to do is to remove the electrons for this whole patch, and then you can do the right program again. But when you are going to remove the electrons from this patch, you cannot remove from only one patch. You need to remove for all the patches in the same block, because the reason is this P subtract, they are shared between the block. So for the same block, they are using the same P subtract. So when you apply the minus 20 volt, it means all the patches in this block will be applied at minus 20. So all the patches will be affected. Okay, so the overhead will be super high. To avoid this super high overhead in the NAND flash controller, the decision will be we don't do the update. Or you can think about like this. We don't do the in-place update. We don't update here. What we are going to do is, you can think about it's more like the remodify write. Okay, we will read out the patch, and then we modify in the DRAM or someplace, and then we write to another available patch. So we don't really need to update those patches already have data. Okay, so this is an example. If this is a NAND flash block, and then there are a lot of patches, usually like 512 patches inside. And if you already program the patch, so how do you know you program the patch?
because if you don't program a patch at the very beginning, at the original stack, all the bit value is 1. 1 means there is no electrons be put into the floating gap. So it should be 1. Then it means like this patch can be programmed. Otherwise, if in this case you can see there's 1, there's 0, there interleave in this patch, it means this patch already be programmed before. So when you are going to do the like second times programming, for example, you say actually there's a 0, you are going to change to 1, there's a 0, you're going to change into 1, like those kind of red stuff. You cannot do it, because if you are going to change 0 to 1 like this, you need to do the erase, right? You need to first erase all the bit to 1, and then you do the program again. But when you do the erase, you will erase all the things in this block. Then the overhead will be super high. So a workaround will be, then you don't write here. You just read out this patch, right? You read out and then you modify in some place, not in the block. Usually it will be in the DRAM for the SSD. So you modify in the DRAM and then you get the new data and then you can write to a new place. So you don't really need to update in the place. So people call them out of place update. You update the data out of the place. So after doing the out of place update, SSD will mark the patch as invalid because you already write the new data to the new place. So the data in this patch is not used. There will be stale. Okay, the stale data cannot be used, so it can be an invalid data. Okay, so that is the case. Okay, actually I'll have one, I would say like more realistic example at the end of this chapter, but let's move on to another topic. Is I think multiple level cells are people usually first know about SSD, right? Because when you are going to buy an SSD from the market, actually you will see this is a MLC, or like this is a QLC, this is a TLC. But what does it mean for this kind of XXLC? Okay, so it means, is it possible to represent more than 1 bit for this floating gap? Okay, what do I mean for more than 1 bit? So before this patch, well, our assumption is there are electrons inside, or there are no electrons inside. So we said there is only 1 and 0 because inside and not inside, right? Okay, but now if we are going to represent 2 bits, which means this area we need to differentiate 4 voltage steps. So 4 means it is not only no electrons or with electrons. That should be like this. If this is 1, 1, then the same, no electron. If this is 0, 0, then there's 4 electrons. But if you are going to differentiate 1, 0, and 0, 1, then you will need to have 1/3 electrons, 2/3 electrons. Okay, so because you are going to control the electrons inside the floating gap in a more sophisticated way, so this one, you need a different way to do the programming. Okay, so when you go to buy an SSD, if you see something called the SLC SSD, and the full name is single level cell, which means each cell there's only 1 bit. And if you have see like there is like MLC, then usually it is implying the multi-level cell. So multiple bits per cell. So the bit number depends on, I mean, it is, if it is the MLC, usually it's 2. So if like TLC, triple level cells, then it will be like 3 bits. So you will have at voltage tables, you need to differentiate. And now people are talking about like QLC is quite popular. When you go to the market, usually you will get a QLC. So QLC means there's 4 bits. So you need to differentiate across 16 level voltage inside this region. Okay, there is a very important thing is no matter how many bits you are going to represent, this space is in the same size. Okay, so because they are using the same size, so the good thing is if you really can represent more bits, for this same size like area, then your capacity will boost a lot. Because come to think about, if you have SLC only, then it means you can only represent 1 bit by this area. But now if you are QLC, you can represent 4 bits for this area. So 4 bits means 4 times. So you can enlarge the overall SSD capacity by 4 times. And actually, the architecture for SSD doesn't change. I mean, most of the architecture doesn't change because this P substrate, control gate, and those here, they are all the same. The only difference is we need some way, the controller needs some ways to control how to program the electrons numbers inside this area. Okay, so I mean, this is a more realistic stuff like 11001 and 00, and this is the different numbers of the electrons inside this like 14 gate area. Okay. Here comes another interesting thing. It's just like if you open some spec or like if you are reading some papers, maybe you will see this kind of figure. So there is things you will see more like the Gaussian distribution stuff, like the normal distribution stuff. Like there is those kind of distributions. And if you look at the x-axis, usually people will say, actually, this is the memory cell threshold voltage. So because like if this is 1110 and 0100, actually, you can get different threshold voltage, right? So threshold voltage is what is the minimum read voltage I can use to read out the data. Okay, so this is the minimum memory cell threshold voltage. So if you are getting different stage, probably the read voltage should be different. Okay, so this you can think about is the static numbers. So interesting thing is the y-axis is number of memory cells. Okay, number of memory cells. So you can think about this figure is telling about if now you have maybe an SSD like you have a 1 gigabyte SSD, for example. And 1 gigabyte SSD, you means like you need to represent 10 to the 9 bits, right? 10 to the 9 like cells. So 10 to the 9 cells, actually, you will have a lot. But now the thing is, if you are going to do the testing, actually you use the same way to do the programming. Actually, this one will become the distributions because there is process variation. I mean, when you are doing the manufacturing, all the cells will not be the same. They will be slightly different. For example, how thick the dielectric layer is, right? Maybe for the neighbors, for this one, maybe because of manufacturing variations, actually there are this one is thicker than this one, and also the P substrate and control gate, like how much of noises they are. So there are a lot of factors that will affect about the even you give the same voltage number, even you give it like 20 volt for all the memory cells, but the amount of like electrons really be pushed inside this floating gas will be different. So this is the reason why like these are all distributions, because by nature those floating gas they look different. So when you apply the same voltage, no matter read or write, actually what you can get a result is like less. Like not all the cells will give you the same results. So this is the reason why in most cases when you open a spec, you can see a lot of distributions. And this is because all the floating gates, they are slightly different between each other, and people call them process variations. Okay, so just another figure about if you have a like TLC, then TLC means you have 9 different stages here. So from 1112 to 000, and it's just about different number of electrons to be pushed inside. Okay, but because this is a basic, I mean, lecture in operating system, so I will not go into the details that you know how to do this kind of stuff. And if you are interested in about how to do the programming and how to read all this kind of stuff, you can take another memory storage system courses. I'll let you know how to do this kind of programming and how to get all the data from this kind of stuff. Okay. So let's move on the next one, because if you have some experience on buying SSD, usually SSD is not that stable, right? Because maybe you buy the SSD for like 1 year or like 2 years, there's error inside. So we are going to talk about the errors part. Okay, so errors part, the title is wear outs and retention errors. So what is wear outs? Wear outs is like this. Okay, this one. Okay, we say when we are going to do the program, it means we are going to move the electrons from outside P subtract into the Fulton gate. And when the electron move across the dielectric there, when the electrons move across the dielectric there, actually it will wear out the dielectric there, because the electron move through this kind of substrate and there are some collision there. So this one will become thinner. And if one day this dielectric becomes too thin, then it loses the capability to capture the electrons inside the Fulton gate, right? So it means the cells cannot be used because the electrons cannot really be captured inside. Then the electron will flee off. Okay, because this one, if it is too thin, then it is not able to capture those electrons. And this is called wears out because it wears the dielectric there. Okay. Okay, so SSD errors means cells contain unexpected number of electrons. So you can also think about if you are using the SLC, this SSD error is not that important because SSD error for SLC, there is a very good tolerance because the number is just about there are electrons or not. So even you have a little bit more, a little bit less electrons inside the Fulton gate, it doesn't really matter that much because this is SLC. So you only need to differentiate two states. But you come to think about if you are going to represent a TLC, there are 9 different states here. So actually, this stage and this stage, the number of electrons between the two states will be very close. So even you get a little bit more voltage for this stage, it will be very similar to this stage. So the same things, if for this 010, the number of electrons, there are some of them flee off from this subtract, then this stage will just become this 011. Okay, so when you are getting a more bits, like QOC things, and there will be more stats, they are very close to each other because the number of the electrons should be controlled in a super fine grain. Then the SSD errors will be super serious. Okay. So retention errors. Okay, but retention errors will be more like a cell cannot permanently retain electrons. So electrons escape over time. So let me give you some numbers. This one is from one paper, and the x-axis shows the PE cycles. So PE cycles means you program and erase. So you can think about if the SSD is 1 terabyte, you program all the 1 terabyte, like the capacity, and you erase all the data. So we will say this is 1 PE cycle. So 10 to the 2, 100 PE cycles means you program the whole SSD and you erase the whole SSD 100 times. Then this is called 100 PE cycles. So and so on. 10 to the 5, it means like you have 100,000 times program and erase. Okay, and the y-axis shows you the bit error rate. So bit error rate means, for example, if you are going to read out a 4 kilobyte data, then how many errors are there in this 4 kilobyte area? Then this is the bit error. You can think about like you read out like 100 bits, but 1 bit they're getting error. So it is quite high. Okay, and there are a lot of plotted lines here. I think very important things is like this 3-year retention errors. So 3-year retention errors is this line. So 3-year retention errors means you put the SSD there and you don't do any program or erase, you just put there for 3 years. You don't really use it. And there is possibility, there's some chance to have error. So if you put there, you don't do anything. So let's say the PE cycle is only 10^2. Just like you only use the SSD for like 100 times. I mean, use the whole SSD for 100 times and you just put there for 3 years, then the bit error rate will be very close to 10^-6. Okay, 10^-6 usually is so-so, because if we say this is bad, then we will say it is 10^-4. If we say it is good, usually it should be higher, very close to 10^-8. So 10^-6 is so-so, not very good, but like not bad. So if you use the SSD for very like intensive, you use very frequent, then your PE cycle will increase, right? Because each time you program the whole SSD and you raise the whole SSD, the PE cycle will increase by 1. So if the PE cycle climbs to 10^5, that means you use the SSD super frequently, and then you stop, you don't use it for 3 years. Actually, the bit error rate will climb up to 10^-2. Okay, 10^-2 is super high. I mean, that means you read any 100 stuff, you will get 1 dose inside. And usually 10^-2 cannot be corrected back by ECC. Okay, so that will be a super big question for this SSD. Okay, so maybe you have one question is then why you don't use the SSD, then why there's retention errors? So there are a lot of aspects, because actually this dielectric layers, it will become thinner because you just put there and there is oxygen, right? There are oxygens, there are some other things by nature. So it is possible this one will become thinner even you don't move the electron across this dielectric layer. But in this time, so this is the reason why it is like in the year label, because in this time to make it to become thinner. Okay, so okay. So if you look at, if we look at the pattern, I mean, someone do the pattern about the retention errors. Actually, most of the retention errors, they are between the stat changes from 00 to 01 or 01 to 10. Okay, so why it is 00 to 01 and it's 01 to 10? Because you can look at this. This is a 2-bit MLC. So there's 1, 1, 1, 0, 0, 1, and 0, 0. So 00 to 01, it means this is a 4 stage, and it dropped back to the 01 stage, which means the number of electrons inside the Fulton gate, they flee off some, right? So because retention error, usually we are talking about the dielectric will become thinner, so it loses the capability to capture some electrons. Okay, so some electrons will flee off. So when the electrons flee off, when they run away, then the state will become a lower state. So the same things, the second highest error count as happens when 01 to 10. Okay, so because this 01 and back to 10. Okay, so this is the pattern just to let you know, because like the electric layer become thinner, so those electrons will flee off. So like this. Okay, so higher PE cycles, because if we come back to this again, here, actually, no matter how many times, like 3-day retention, 3-week retention, 3-month, 1 year, 3 year, no matter which it is, it depends on the PE cycles a lot. Because if you have a high PE cycles, no matter what you are using, what kind of like retention or like read or like write, read or erase, actually the error rate increase. And the reason is PE cycle means you write the data, which means you push the electrons inside the cells, and then you erase it, you drag it back. So for the dielectric layer, it needs to suffer from twice the movement. Okay, so like this, there's a lot of movement between the dielectric layer, and this one will become thinner. So one day they cannot be able to capture the electrons. And there comes another issue. So how to estimate the lifetime? Just like how do we know this SSD is healthy enough? So there are two ways. One is called PE cycles, another is bit error rate. So PE cycles, I would say it is an implicit way. The reason for implicit way is it is easier to collect, right? PE cycles is you can count, okay, this block you erase, you program maybe 100 times and erase 100 times, then PE cycle is 100. Okay, but the reason I say this is an implicit way is actually for each cell, there are process variation. So even they are endure the same access like 100 times, but they will have different reflections on the dielectric layer. Maybe someone, they're super healthy because their dielectric layer at the very beginning is super thick. So even there's having like 100 of PE cycles, it only like wear out very portion of it. So it doesn't really matter. But maybe for some other cells, because at the moment it is manufactured, its dielectric layer is already thinner than others. So in this case, if you are enjoy the same PE cycles, then probably you will have more problem compared with those dielectric layer is thicker one. Okay, so PE cycles is only to that the user programmer or like something the system maintainer to easily know if the cells is still healthy or not. It's just an indicator. So a more accurate way is use the bit error rate, because bit error rate is when you read out the data and you can, I would say like 100% make sure how many errors are there inside. So if the bit error rate is super high, it means okay, actually most of your cells actually they're out of order because each time you read out the wrong answer. Okay, so bit error rate is an explicit one. So if you use a bit error rate, you can totally know, oh, actually that cells they're getting out of order, and that patch is super healthy because the bit error rate is super high. Okay, so this is two different way to know how is the lifetime. So here is a table to show you different types of like SSD model. This is SLC, one cell, 1 bit. MLC, usually one cell, 2 bits. And TLC, one cell, 3 bits. QLC, one cell, 4 bits. So you can see actually here the PE cycle has a super wide range of difference. For SLC, actually, SLC SSD can endure up to 90K to 1000K of the PE cycle. That would be a lot. So when you look at a QLC, actually it can only endure 500 to a K, 1000 times of PE cycle. So if you compare SLC and QLC, actually the PE cycles endures level can be like 3 orders difference. Like SLC can endure like 3 orders time of the data compared with the QLC. Okay, but like, I mean, QLC is larger than SLC because you have a more bits per cell, so you can store more data. So it's just a like decision about you are going to have a larger capacity or you are going to have a more healthier cell. Okay, so let me quickly wrap it up for the SSD part. Before this slide, we talked more about the cell level stuff. Just like in a patch, there are a lot of cells, right? So it depends on for the cells have 1 bit cells, then you have 4 kilobytes of the data inside. But if we zoom out and if we look at a whole SSD, then it will be like this kind of stuff. So inside the SSD, there is a controller, and there is DRAM, and there are NAND flash chips. So inside NAND flash chips, there are block, there are patch, there are cells. So we are talking about this level stuff before this slide. But for the SSD part, actually, very simple. Next week, there are Phison, right? Phison, they are doing the SSD controller design. So most of their technologies, they're focusing on this kind of flash translation, their design part. Okay. And maybe your question will be, then who is doing this kind of NAND flash cells? So for example, Samsung or like SK Hynix, they are doing this kind of cell level design. Okay, flash translation layer, and then memory technology device MTD layer. So flash translation layer, you can think about it's a
more like, you can think about it is a little bit like the operating systems for the SSD, but it is not the same things, because operating system, that is more broader concept. You are like managing the process and the memory stuff, but the SSD controller, I would say like it is more like the middleware for FTO to control some metadata stuff. And MTD usually is quite intuitive, because MTD is going to control how to interact with the NAND flash chip. So I mean, you need to follow some protocol to access the NAND flash chips. So, okay, the reason why we need an FTO is SSD, we say the erase unit is larger than the write unit. And each time when we are going to write the data, we need to first run the erase to make the patch back to the origin state, to make the cells in the patch becomes like 01, like there's no electrons inside our cells. Okay, so we need the sequential write constraints. Okay, but sequential write constraints need some metadata to maintain. So what do I mean need some metadata? Given an example, this is called NAND flash block 1. So there are a lot of NAND flash patches, right? Okay, so for example, for each NAND flash patches, there is a physical block address. You can think about it just very similar to the physical address in the SSD. In the operating system. So for the operating system, the physical address is for the DRAM, right? If you still remember, like each patch frame, they have their like physical address. So the same thing here for a NAND flash. Actually, in each NAND flash block, you have a lot of NAND flash patches. So for each patches, you will get a number, and it is according to the physical layout. So physical block address, for example, this is 800. And there is another thing, it's called logical block address, LBA. LBA is also very similar to virtual address, but the function is not the same. The function is like this. Okay, if you have a patch called PBA 800, okay, and you are going to do update, but as we mentioned before, you cannot directly update here because SSD cannot support in-place update. SSD should use the out-place update. So out-place update means we need to read out the full patch and then do the modify. We modify to this kind of step, like 111011, this kind of step in a DRAM, and then we will write it back to another available space in different locations. So probably, for example, if there is a free allocations on the second patch of block 2, so you will move to here, okay? Then what the FTO it will store is, hey, actually, your LBA 500 is not mapped to the PBA 800 now, because in your SSD, we help to move to other place. So the PBA 800 it will be changed to PBA like 1201. For example, if this is 1201, then the LBA 500 will change to 1201. Okay, so this is what FTO does. But maybe your question is why we are going to do this kind of stuff, why we're going to do this mapping stuff. Because if you are a user, if you are using your SSD and you are going to write the data to a SSD, actually, before this class, I believe most of you guys do not really know there is this kind of out-place update stuff, right? And because you don't know the out-place update stuff, but actually the SSD still works. And the reason SSD still works is SSD hide those kind of management inside the controller. The controller will help to manage those kind of write stuff. So even you are going to write the same LBM, you are going to write the same like file several times, it still works. And it doesn't really take too much of time. Okay, and the reason is the controller inside SSD, it runs the FTO to maintain all this kind of stuff. So it hides the complexity of SSD for the user. Okay, and the reason how the methodology how it hides is this kind of table making stuff. Actually, because we are going to do to follow the sequential write constraint, so we need to change the physical block address. So the next time, if the user first write the data twice, third, maybe 4 times, and the next time the user going to read out the LBA 500, SSD can return the correct patch to the user. Okay, and the user doesn't really know actually the physical block address changes because the user can only know the logical block address.
Okay, those the user only know, okay, I'm going to get a file. So the file system will translate into the LBA. And so this is what the user only know. And PBA, this is only maintained by the SSD controller. Even the operating system, it doesn't really know how SSD works because the operating system will only send the LBA to the SSD. So the SSD controller will do its own management to link this LBA to a correct PBA. So this is how the SSD works. Okay, so after doing this kind of movement, actually, SSD controller will mark this patch as invalid. So it only marks as invalid. It doesn't really erase it. So mark as invalid, you can think about maybe there is a bit here, and then the bit say, hey, this is invalid. Just that's it. So we don't do any extra to do the erase or to do some other operation and for it. So because there will be more patches becomes invalid when you use the SSD for a longer time, because you probably will do a lot of write to the same, data or like something like that. So probably there will be some amount of the invalid patches inside the H block. So one day we need to do a thing called garbage collection. Garbage collection is if there are too many patches in this block becomes invalid, then it wastes up too much of space, right? So one example is if half of the patches in this block, they are invalid, which means you sacrifice half of the space because invalid patches are the patches you cannot use. Okay, so a workaround solution is the garbage collection, the FTO, the controller will read out all the valid patches, all the live patch to some other patch blocks, and then you can erase it. Okay, so this is just like a very close to a remodelable write, but it applies to all the live patches inside a block. So you can finish a garbage collection, but you can tell because you are going to move all the live patches. So the garbage collection is very time consuming. You need to, it will usually occupies a lot of SSD bandwidth, inner bandwidth for this kind of live patch moving stuff. Okay. So let me show you a very brief, like how SSD get a data from NAND flash chips. So once the SSD controller get a request from the operating system, device driver is part of the operating system. So you can think about this is operating system, and it sends a request to say, hey, please return me the LBA 500, right? So the controller gets the LBA 500, and the controller will run a translator. So the translator will check the translation table inside DRAM to check about, hey, LBA 500, where it is. So maybe it is PBA 800 or something like that. So after getting the PBA 800, then the FTO can get the data from NAND flash chips according to the PBA 800. So FTO will ask the MTD, and the MTD, there is some protocol to translate the PBA 800 to which, according to architecture, which channel, which die, which plane, which block, which patch, like that. So after getting this kind of information sent to the NAND flash chips, the NAND flash chips will return the data according to the PBA 800. Okay, and after that, if some days the FTO is going to run the garbage collection, the same things as FTO needs to ask the address translator, because in most cases, FTO only know which patch, which LBA is valid. Okay, so once again, the garbage collector will interact with the address translator to translate all the live patches to their physical address. So the garbage collection can do the, live patch copy stuff. Okay, and when we are doing the garbage collector stuff, actually there is a extra task SSD will usually does. It's called wheel leveling. Wheel leveling depends according to the wording. Where means it is going to, it is going to make the dielectric become thinner. This is called a wheel, right? And leveling is we are going to distribute all the, wheels to all the cells. So wheel leveling, you can think about it's going to distribute all the write to all the cells. So in this case, no one patch, no one cells will become a bad cells before all the cells
becomes the best cells. Okay, so without real leveling, you can think about maybe you frequently access one patch, for example, then this patch probably will get a super high wear out. Then the patch will get worn out if it exceeds some PV cycles, right? But the rest of the patch in the block, maybe it is super healthy because the SSD only access that patch. So the real leveling is SSD will control, it will distribute all the assets to all the cells to absorb all the assets. So the SSD cells will become worn out at a very close time. Then it can extend the lifetime. Okay, actually, we don't have time to go into details about the garbage collection and releveling. So the same things, if you're interested, we have another course to talk about those kind of, algorithm and data structure for this each of the component. Okay, so that is for the SSD part. Okay, so we finished the device. We talk about the hard disk drive and SSD. So the next thing is the device driver. So device driver is, if you still remember here, we say upon the SSD, outside the SSD, when your CPU is going to interact with SSD, CPU usually will run the device driver. So device driver is also a part of the operating system. So here, actually, the yellow part and the green part, they are all belonging to the operating systems. And the gray part is a device, okay? So if we are going to do the interaction with the peripherals, we need to use a device driver. So there are a very large amount of device drivers in the operating system. For example, you are going to interact with the SSD, hard disk drive, like your CD-ROM in the ancient time. And if you have other like monitor, mouse, keyboards, each of them, they need their own device driver. So CPU use two different ways to interact with the peripherals. One is called port mapping. The other is called memory mapping. So let's first talk about the port mapping. So the definition is CPU access peripherals by in-out instructions. Okay, peripherals means like those kind of like keyboard, mouse, disk. So you can think about those stuff, they are attached with the southboard, they are peripherals. So which are not peripheral is, for example, DRAM usually is not a peripheral because it is super fast, so it is attached to the node bridge or like the memory controller now. Okay, so for a peripheral, usually we call it I/O device. And for port mapping I/O, actually CPU will separate the memory address and the I/O address. So memory address is the physical address part. You already learned in the physical address management part. So when the CPU is going to interact with the I/O device, because for example, I/O device will map their address to the CPU. CPU can know if we are going to get some data from the hard disk to get from there from the SSD, we need to know which address that we are going to get. So this kind of address accessing part, CPU will have a unique instruction code in and out. Okay, so this is called a port mapping I/O. And actually, CPU will use a, typical way, level sort to access the memory. This is what you already know. There is another, and I think this is like people be more familiar with, it's called the memory mapping I/O. So the memory mapping I/O is, it integrates the I/O address space with the memory address. So let's say we just partition part of the memory address space for the I/O. So the I/O device can map their mapping table to the memory address. So CPU only use those to access. There is no in-out instructions. So maybe you have a question, which are like people usually use now. I will say memory mapping I/O. So the reason is in memory mapping I/O, you only need to sacrifice part of the memory address. Then you only need one kind of instructions. So because if you are going to support port mapping I/O, you need to have two different kind of instructions. So you need to change your instruction set to support this kind of port I/O mapping stuff. So you need to pay for any extra like power, CPU, like overhead. Okay, so you can think about this one, you need extra CPU change overhead for the ISA. And this one, you need to sacrifice part of the memory address space. But in current time, because you have a lot of memory address space, if you are using the 32 bits, then you have 4 GB.
then if you have like way more, like if you are using a 64-bit system, you can address to a super large, like several terabyte. And usually you only have like 16 gigabyte of the memory, right? So you can think about 16 gigabyte, you can sacrifice like, for example, like 100 of megabyte for IO. They are super decent there. So it doesn't really sacrifice too much in this case. Okay, so this is the reason why memory IO is quite famous now. And the last thing is DMA. So DMA is different from, well, port memory IO and memory IO. That's very different idea. DMA is like this. When CPU is going to get the data from IO device. So if there is no DMA, CPU should read from the IO device and then move to the memory. Okay. So the more data you are going to move, then the more time CPU should delay here. And CPU cannot run other things because CPU should monitor the transmission from IO device to memory. And DMA comes in. DMA is kind of a DMA controller. So you can think about DMA as a microcontroller. It's a very tiny CPU. What it helps is CPU will tell DMA to say, hey, actually, please help me to move, for example, this region to this region. And the DMA will move it one by one, just like a watchdog. DMA will watch out to check about if the memory address is correct. And then CPU doesn't really need to wait here. CPU will go back to do other stuff. Okay, so this is the good things for DMA. Like it's just like you spend a little bit extra overhead for this extra hardware device, and you can relieve the overhead for CPU. All right, so I think it's time. So let's call it a day. Thank you guys.
就是第4个，就有看到它是从这里然后这里，那因为大家讲的好像都是它会漏，它会有一些从这里跑到这里，
没错，
对，那为什么会有这里跑到这里的事？
因为有些时候它是因为温度的关系，就是 SD 的 cell 它的活跃程度跟温度有关系。那你温度改变、湿度改变也会导致它可能会，因为它变薄了，所以它有可能电子就流失会进去，这样子。所以它其实是双向的，只是大部分的情况电子会趋向往外跑，这样子。
那是因为这里，因为我们如果没有加任何电子的话，这里会比较中性。
对，所以这里的几率会小很多。
所以这里跑到这里几率比较大是温度。那如果你说如果电流来，如果从这里过来的话，它会有可能跑，
对，
有可能跑，
有可能，没错。所以这边跑上来有个原因，有可能是因为你其实没有动这边，可是你周围的人做了
对
program，周围的动 program 它就可能干扰它就有可能会导致这边被激发出一些电子会把它跳跃进去，这样。但你这边其实都没动，因为你只是你周围的人在做顺序而已，对，所以才会有那种什么保护电压这种措施。可是保护电压也是一样，因为你保护电压，你这边就会被激活。只要你这边够薄的话，你就算这边只有5伏特，你还是会有机会电子跑进去。对，
sorry, I have a question. So DRAM is volatile, right? So after we see the translation, there will be
Molecular number chips. When you are going to power off the DRAM, the DRAM translation table will have one version on the nameplate chips.
Yeah.
So you can think about like actually when you power off the SSD, if there is a power, then the data from nameplate chips, the translation table will be first moved back to the DRAM.
Oh.
So there is a version on the nameplate chips for this table.
So the translator in the FCO level cannot directly access to the mapping table.
It is possible, but I mean it is slow. So usually if there is in the DRAM, then why not just directly access the DRAM part?
Oh, DRAM is faster.
Yeah, DRAM is quite faster, like I would say like 3 orders faster.
Oh.
Yeah.
Okay, that's all. Thanks.
Thank you.
Thank you.
Thank you.
请问启动前机应该好，我记得上一次
应该
课后
还没。
哦还有
对，我猜应该是这礼拜的某一天，反正他们应该会公布，直接请你们去。对，所以我们上课里面是不会讨论。
哦 ，OK，
对，
我想说上次上课
对，
下课的时候
应该还没，我看他们助教有些好像还有部分没改完。对，谢谢。
好，感谢线上的大家，Thank you guys online. See you next week.